Yeah, so hi everyone, thank you for attending. I'm gonna talk about the Xen system boot attestation using TPM2 and DRTM. So I'll briefly describe what the TrenchBoot project is, who contributes to it, what we have already achieved, and what we plan to do, and about the safeboot. So this is quite recent, let's say, utility that helps with TPM2 attestation. And I will show you how it works, maybe some demo and problems I have faced, and what modifications will be needed in the future to the Xen. Okay, so a few words about me. I'm Michał Żygowski. I work for FreeMDev Embedded Systems Consulting, and I'm a firmware developer, mainly interested in coreboot, security solutions, and advanced hardware and firmware features. They maintain Braswell SoC, PC engines, and Protectly platforms in coreboot. So what TrenchBoot is? So TrenchBoot is a cross-community integration project focused on launch integrity. So that means we don't have a single project or a single kernel or something like that that is called TrenchBoot. We deal with various open source projects like GRUB, Linux kernel, and Xen to integrate the dynamic root of transfer measurement technology. And the name for the TrenchBoot, as far as I have learned, is play of dealing with the MUD mess of trying to find a way to unify the boot integrity. Because as you may know or not, the DRTM technology is not so unified. Although we have specifications for that, various vendors implement it quite differently. So TrenchBoot also wants to unify the approach to have the most similar launch integrity process all over the architectures. Okay, so who contributes to TrenchBoot? So first of all, Daniel Smith from Aperture Solutions is the founder of the idea of the TrenchBoot. He started his work a few years ago. And besides Daniel, we have also Citrix. For example, Andrew Cooper helped us with TrenchBoot. People from FreeMDev, for example, are doing the AMD part with Andy's help. TrenchBoot, and there we have also Oracle and Intel, which works on the Intel TXT implementation of the TrenchBoot. And what I also mentioned that FreeMDev is a beneficiary of the NANET Foundation Next Generation Internet Grant for the privacy and trust enhancing technologies. And thanks to them, we were able to push forward the effort of AMD DRTM even more rapidly. Because until recently, we have been doing that pro publico bono. So what we have already achieved, I will just cite a few presentations. First one from Daniel P. Smith. So TrenchBoot was born out of limitations of using T-boot to launch Xen because we had no alternative to T-boot and Intel TXT, and there was no even single implementation for the AMD Secure Startup. So a few months later, Piotr Król from FreeMDev presented on open source firmware conference an open implementation for DRTM for AMD platforms. So not so long ago, so we had a working implementation for AMD. So from the 2018, where there was a briefly an idea of the TrenchBoot, we have managed to achieve quite quite many things. So if you want to track our progress on the AMD development of the TrenchBoot, you may visit our blog and the tag TrenchBoot. So far, we have been able to test the AMD DRTM and TrenchBoot on various AMD processors. Like we have validation of family 16 on G series embedded SoC and some Ryzen and EPYC processors from the embedded series also. We have set up some continuous integration and continuous deployment for TrenchBoot related projects. So we have the Meta TrenchBoot, which we built some Linux distributions with already enabled TrenchBoot. We have say for our GRUB2 modifications for Linux kernel and the landing zone. The landing zone is a software that is similar to the Intel authenticated code modules that are required to launch the DRTM. We have also made available the DRTM via network boot using iPXE. We also support some legacy and UEFI environments. But UEFI multiboot 2 is not yet tested and verified. Recently, we have also added some TPM event log support. So we expose a DRTM ACPI table that holds the location of the event log, which is used in the TrenchBoot to store the measurements of various components. And what is most important, we can also launch Xen in legacy boot mode with TrenchBoot. So this is what we achieved, but the following roadmap was prepared also. So in August, we plan to improve the security and measured launch process in the Xen hypervisor for the TrenchBoot, because currently we're lacking few security measures to make it as secure as possible. And in the November, we plan to set up some kind of remote attestation server proof of concept with TrenchBoot and IETF remote attestation procedures. And what is left is to upstream the whole work we have done so far. There are already some RFC patches you may find on GRUB with the Intel TXT secure launcher, and we have the modifications of the TrenchBoot secure launch Linux kernel support. So in order to show you the TPM2 attestation, I have decided to use the safeboot. It's a utility to boot Linux safely. And it has 5 main goals to ensure the safety of the boot process of Linux on normal laptops. First of all, it ensures that we are booting only the code that is authorized by the system owner, because we have installed, because safeboot installs a key, owner key to the UEFI secure boot, which is used to sign the kernel. The root file system is encrypted to ensure more security, and its key is stored in the TPM, and it is only unsealed when the firmware and its configurations are modified. So we rely on PCRs to seal and unseal the key. Safeboot also focuses on reducing the attack surface. For example, by protecting the disk contents, encryption, we have dm-verity, we have LVM also in place. Everything just to reduce the risk of the attack from even with person with root privileges. And we prove to the remote attestation systems that the local machine is safe using a remote attestation protocol for the TPM2. But this is how original boot safeboot looks like. So we have some parts marked on red, which are quite confidential, like secure boot, boot guard, or hardware validated boot. They are typically tied to the onboard secondary processors like Intel Management Engine or AMD Platform Security Processor. They are optional and can verify our firmware, which is UEFI. The blocks on yellow are marked as components that are not necessarily open, but we have specifications which tell us how these components behave. And then we have green open source blocks, which are known to the public, and we have fully control because we can always rebuild and modify these components. And we have the attestation server. So I didn't give any color because it is choice of the owner how to make the attestation. So when we start with the firmware, it has the UEFI secure boot keys enrolled by the owner, which were used to sign these files. These files are packaged Linux kernel, initial RAM disk, and command line into a single EFI file. And we have two of those in case the mainstream file is not verified correctly. We have the recovery, and then we have the root file system. Root file system is encrypted by the kernel with the keys stored in the trusted platform module. And based on the platform state, so the PCRs, we either unseal or not unseal the key. And then if we are booted to the operating system, we may perform the attestation. So we request the TPM to prepare a signed quote based on the platform state, and we send it to the attestation server to verify it and tell whether the platform is in a trusted state or not. This is my custom boot flow I have come up with. So we are not relying on every component that original safeboot provides. Instead, we have more open hardware like PC Engine IP2 with AMD G-Series embedded SoC. We have TPM 2.0 from Infineon, and we have open source firmware coreboot. So how the integration, how this boot process can look like. So we also have this CPU chipset and SoC, which not always is trusted, or rather, not always we know what's inside. And this is the red block. We can have the hardware validated boot, for example, and then we have the coreboot. Coreboot is an open source firmware framework, and PC Engine IP2 is supported by coreboot, and we can have the UEFI secure boot equivalent, which is verified boot. It also relies on signed firmware components that are verified during boot process, and we can also have a support for measure boot, so we can utilize TPM to measure the components. And then if we are done with the bootstrapping process, we also we just jump to the GRUB, which is the most widely used the bootloader. And this GRUB is slightly modified because we have here the TrenchBoot secure launch support compiled in. So we are able to launch the DRTM with this GRUB. So in case of a multi-boot 2 process, modified multi-boot 2 process with secure launch, the GRUB hands over the control to landing zone. Landing zone, as I mentioned earlier, is a secure launcher block for the AMD secure startup. So when we invoke the security instruction, like a SKInit, it jumps to the landing zone, which performs the secure measurements of the kernel and software we are trying to launch. The security is ensured by protecting this landing zone from any DMA attacks, and hardware inhibits all interrupts in the secure boot process until we say, of course, that we have measured all our components and it is safe to release the interrupts. So When we finish with the measurements, we launch the Xen hypervisor and Dom0 Linux kernel, which also does the decryption of the root file system based on the PCRs. But this time we are using the DRTM PCRs to unseal the LUKS key. And then if we are booted into this final system, we of course also prepare a signed quote for the attestation. But also in this case, we are using the DRTM PCRs, not these from the BIOS. And then we send the quote to the attestation server, which then responds with an answer whether the platform is trusted or not. So how this attestation looks like. Safeboot offers a script that leverages certain TPM 2.0 features, which may be quite hard to understand without some deep TPM2 tools knowledge. But in short, what it does is it prepares an attestation quote. It can verify it against the signature, because each attestation quote must be signed. Attestation quote also may be verified against event log, against the endorsement key, whether it is provided from valid TPM. And also this script offers a quote-based sealing and unsealing of the secrets. If you want to read more, you may read on the safeboot page about the TPM2 attestation. And the same script is used on both the attestation server and the attested platform, because it has some sub-commands to create the quote and to verify the quote. And to attest the platform, it is just sufficient to invoke two commands. And first one, we may just generate the quote based on the knowns we get from the server and the PCRs, which may also be get from the server. And then we just move the quote to the attestation server to verify it. So how booting looks like with DRTM on AMD platform. So as I mentioned here, we have the modified GRUB 2 with TrenchBoot secure support, secure launch support. And what does it mean? TrenchBoot support adds two additional commands to the GRUB command set. It is slaunch and slaunch module commands. They are used to indicate the GRUB that we want to perform a secure launch, and it selects the module that is used to execute DRTM. It's either Intel ACM or the landing zone. And the slaunch tells that we want to secure launch. Yeah, so if these two commands are present in our GRUB configuration file, it hooks into the Linux or multi-boot to boot protocols to set up the environment, the DRTM module, and the TPM, and then executes the security instruction for given architecture. For the AMD case, it is a SKINIT instruction. And then the boot process is handled over to the landing zone. This, as I mentioned, is a secure ladder block described in AMD architecture programming manual. It is 64K big, and it is executed after issuing the SKINIT and measured into PCR 17. We use the landing zone to measure the main kernel, in case it may be Linux kernel or Xen hypervisor. It depends on the boot protocol we use. And then landing zone hands over the control to the kernel or Xen hypervisor, which is already measured and loads Dom0. And then when we are already booted, we want to create a quote for the attestation. So the TPM2 attest script will read the endorsement key from the TPM. An endorsement key is a unique key that is signed by the TPM manufacturer. Its private part never leaves the TPM, so it's protected. and we read the public part to include it in the quote, which will be later verified whether the quote and the key comes from a valid TPM. Then we create a ephemeral attestation key, which is used to sign the quote which we will soon generate. And then we request a quote from the TPM, which is signed with the given attestation key. And we also attach the TPM event log for additional verification of the PCRs. Such generated quote is later sent to the attestation server. And on the server side, we use also the TPM2 attest script, which unpacks the quote and verifies the signature of the quote. So the public part from the quote is used to verify its signature. It additionally verifies the event log by calculating the PCRs that should match those included in the quote. And we optionally may verify the PCRs in the quote and event log against known good PCRs. However, I haven't been able to do that because safeboot didn't document any format about the file that represents the good PCRs. And then at the end, we verify the endorsement key in the quote, whether it comes from the valid TPM. And in order to do that, we have a trusted root CA with all the certificates from the TPM vendors, and against it, it is validated the endorsement key. So I would like to show you some demo. So I will share my screen for a second. Okay. And here I have a terminal of IPU5 platform. It's a variant of IPU2. And it's just, for example, read with the platform to show you that the LUKS key is automatically unsealed. So we have a open source CBIOS here, as you may already know it from Xen. It is also used to launch Quest VMs. And now I launch the Xen with a secure launch option. It will take a while to execute it. I'll try to stop at the point where the key is unsealed. Show you how it works. Oh, yeah, it's here. Although the unsealing script doesn't show all PCRs, it is shown that the TPM disk key has been unsealed. So it means that our PCRs that we have sealed the LUKS key to were matched. So I'll show you that DRTM PCRs are really extended. So here we have the DRTM PCRs. It is PCRs from 17 to 22, and we see that 17 and 18 is extended. And these are the PCRs I have sealed the secrets to. So let's generate the quote now. And how the comments look. We use the TPM2 attest script, and we use the command quote to generate the quote. Another argument is deadbeef. So it is a arbitrary nonce I have selected, and we want to use the PCRs 17 and 19. So here we see that the TPM attestation script has read the endorsement key. It creates now the attestation key and generates a quote. Additionally, the script locally verifies the quote signature in case it would be modified somehow before sending to the server. Now I will send the quote to another machine, which will serve a role of the attestation server. Now I will use the verify subcommand of TPM2 attest to verify the quote. So it basically unpacks the quote and checks its signature, verifies that the PCRs calculated from event log and those from quote are matched. As we can see, they are. And then we validate the endorsement key certificate against the certificates of the TPM vendors. And we see that we have matched the Infineon Optiga TPM 2.0 certificate, which is valid because we use Infineon TPM 2.0. Okay. So that would be it for the demo. And a few issues I had to resolve before I could put everything into pieces. So first of all, the current TPM tools packaged in distributions are not yet good enough to perform the attestation, so one has to use the most recent versions. And I have noticed that between some of the versions, certain environment variables required for access to the TPM changed its name. So yes, I had to debug it for a while before I get working the TPM2 tools. Also, I had problems with LUX key unsealing. Although I have verified that my PCRs aren't changing, there was a matter of sorting these PCR digests into ascending order before I pass it to the sealing script. And the package released on the GitHub did not, for example, contain all the scripts, so I had to clone them manually and copy the scripts to the correct locations. Yes, TPM2 command not found means that I have been using too old version of TPM2 tools, so I had to compile myself them from scratch. There were some also issues with event log parsing scripts in safeboot, which I also had to fix. And as I said previously, there is lack of reference good PCRs file that I could use, for example, on the attestation server side to verify the PCRs against. And what is more important, we still need certain features to be implemented in TrenchBoot. For now, the Linux kernel and initial RAM disk is measured before Xen is launched. So we measure all multi-boot modules in landing zone, although it should be rather done just before execution, because in the midway someone could modify the contents. We need to add the protection against DMA attacks for the memory where the kernel and modules is placed, also for the Xen hypervisor, and preferably using IMMU, because currently we have only protection which is based on the device exclusion vector. It is a hardware mechanism that blocks the DMA for the initial 64 kilobyte block. So the landing zone is protected, but the rest is not for now. And we need also some easy way to access the TPM event log for DRTM. Currently, I had to use some modified Linux kernel just to access the coreboot tables to retrieve the log from the DRTM. And also, as probably was mentioned by Daniel in previous presentation, we would like to have the DRTM late relaunch, so we can relaunch our software and remeasure it at any time. And preferably, we would like to have also DRTM for virtual machines. So an implementation of emulated DRTM would also be cool. But these last two are quite long-term items. And yeah, these are the references of the code I have used, just attaching for reference. And if anybody would like to see and try it himself, here you are. And a quick summary. As shown, it is quite hard to achieve reasonable security. One has to go through issue resolving process before everything is gonna work. We are getting quite closer and closer to the state where the security will be widely available and easily, but there's still a lot to do to make it working out of the box. And I think this is a kind of breakthrough in platform integrity and security area, because nobody has shown a TPM-based attestation either, I think. So safeboot is the first one to show the attestation based on the BIOS as CRTM, and we have the first DRTM-based attestation. And of course, there's a need for more open projects like TrenchBoot, CubesOS, etc., which focuses on the security, privacy, integrity. Because without it, we'll be still far away from the desired state. And I would like to thank you, Daniel Smith and Andrew Cooper, Christian Hebel, Piotr Kru, that helped with developing the TrenchBoot. Also, would like to thank Rich Persaud, who gave the idea to present this TPM2 attestation, and Daniel Kipper, who is a GRUB maintainer and helped me a little bit with the integration of GRUB here. Okay, and that would be it. Thank you, and I'm open to questions. Thank you, Christopher. Yes, improving security of Xen boot. I mean that we need, for example, to maintain or extend the protection on DMA of the multi-boot modules. So as I said, on the only protected component is now the landing zone. So before the Xen launches, we need to cover with the protection the Xen hypervisor kernel and the DOM0. So at this point, it is open to various attacks like the DMA or even later the interrupts. What is more, as I said, the interrupts are inhibited after SK unit. At some point, this interrupts needs to be released. So then, as far as I know, then sends the self NMI at some point. So by this time, the interrupts either should be released or should be handled differently in Xen. So currently, it is a rather proof of concept implementation of multi-boot DRTM. So before we hand over the control to Xen, we just release the interrupts in landing zone. So this is kind of also open for attacks.
Just to add to that a little bit,
Yes, Andrew.
the way this is expected to work is a little bit like how tboot currently works. Tboot is the Intel version of this, essentially, but TrenchBoot is trying to do it in a more upstream way. The requirement basically is that each step which loads the subsequent step has to set up DMA protection and has to measure the binaries into the TPM and update the event log so the later system can verify what happened. From Xen's point of view, this means having an entry point that's compatible with the common DRTM entry point that is currently under some vehement discussion upstream in Linux, which will allow GRUB or any other compatible bootloader to start Xen in this mode. We would also need Xen's IOMMU implementation to also be able to take over from a live running IOMMU that already has protection set up in place.
Yeah, so we need also some handoff, right, from the bootloader to Xen with how IOMMU should be configured.
To be honest, it will be much easier to get to a point where the driver is capable of coming up, figuring out what's currently enabled and what changes it wants to make without interfering with the current setup. Because you also, for example, need a similar situation for kexec if you want to safely kexec with DMA going on.
So which... I think Roger was first. Which entry point do you have in mind? Is this the Linux kernel entry point, or? I think Andrew mentioned the entry point of Linux. So the Linux entry point is used with TrenchBoot for the Linux boot protocol. So it is a modified entry point that is used by GRUB when we have the secure launch enabled and requested. So we jump into a slightly different place in kernel, which also does the early measurements there. So currently for Multiboot 2, there is no different entry point.
In reality, whatever we end up doing will be something close to how Multiboot 2 entry currently works, because it's almost like we designed that because it was easy.
Yeah.
Yeah, I mean, go ahead, Roger.
No, I mean, I just understood from Andrew's sentence before that we need a new entry point. That's going to be different from the current Multiboot 2, but I'm not sure I got that right.
Yes.
Okay, I meant new entry logic, I suppose, more than strictly speaking a new entry point. But
we may also try to detect whether we have been launched by a DRTM event. Yeah.
Yeah. So the key point here is this is what drove the new entry point we put into Linux, is that when you come through the DRTM, the CPU is going to be in a totally different state than what it would have been given to you from a normal bootloader handoff. So so as Andrew said, it's not necessarily for Xen. It doesn't have to necessarily be a new entry point. It just has to be a new set of logic to handle a different state of the system than what would have how GRUB would have normally handed it to you, or whatever your bootloader is.
You've got weird things like under Intel, you've got to use the senter instruction to bring your APs out of the mode they're sat in, because you can't send NMIs to them, for example. So there are changes to the boot logic required depending on which vendor you're on and how the earlier step in the system set it up.
Okay, but just adding something like a multi-boot 2 flag or something like that should probably be enough for us, I guess. I mean, we don't really need to change the early entry point. I guess that would be fairly similar.
To a first approximation, no. I think we've got to avoid doing things like placing the trampoline in low memory until we've started the IOMMU. But we can do that anyway for other reasons. So one of the Amazon live update patches is trying to do that. So there will be some changes to our general logic, but we can make it work.
Okay, any other questions? I guess not. We're quite on time. 2 minutes left.
In which case, thank you for the presentation.
Yes,
Yeah,
thank you.
Thank you very much.
Yes, thank you, Daniel, for invitation to this event.
No problem.